Welcome back to the podcast, everyone. Today, we're diving deep into a fascinating paper exploring the frontiers of image generation. It's all about a novel approach to representing images called 1D tokenization. Joining us today is Dr. Chihang Yu, lead researcher on this project, and Professor Daniel Kremers, a renowned expert in computer vision. Welcome, both of you.
Thank you for having us. It's great to be here.
It's a pleasure to be on the show. This is a truly exciting area of research. Dr. Yu, let's start with the basics. Can you tell us about the current landscape of image generation? What are the key challenges, and how have things been evolving?
Sure. Image generation has made tremendous strides in recent years, thanks to advancements in both transformers and diffusion models. We've seen remarkable leaps in generating photorealistic and even artistic images. A crucial part of this process is image tokenization. This is where you transform an image into a sequence of tokens, which are essentially compact representations of the image content. Think of it like translating a full sentence into individual words. This process is essential because it simplifies the task for the generative models, making them more efficient and effective.
So, what's the problem with the traditional approach to image tokenization?
The current methods, like VQGAN, are based on 2D grids. Each token represents a specific patch of the image, maintaining a direct correspondence. However, this leads to some limitations. First, it doesn't efficiently handle redundancies in images. You see, images often contain similar patterns and features in adjacent areas. This redundancy is wasted with the 2D grid approach. Second, this fixed grid structure restricts the flexibility of choosing the latent size, the number of tokens needed to represent the image. This is where our approach comes in.
Professor Kremers, can you elaborate on that? Why is this a major obstacle in image generation? Imagine you're trying to build a model to generate a high-resolution image. The existing methods are like trying to construct a complex structure with oversized bricks. You're stuck with a limited set of sizes and shapes, which restricts your ability to create something intricate and detailed. It's inefficient and ultimately limits the quality of the generated image. So, Dr. Yu, you're proposing a different approach, a 1D tokenization method. Could you tell us about this breakthrough?
That's right. We introduced TiTok, which stands for Transformer-Based One-Dimensional Tokenizer. Instead of a 2D grid, we represent the image as a 1D sequence of tokens. Each token doesn't correspond to a fixed patch, but can represent regions across the image, learning more semantic information. This approach allows us to significantly reduce the number of tokens needed to represent an image. And the best part? It still maintains or even surpasses the performance of previous methods. We can now generate high-quality images with as few as 32 tokens, while existing approaches often require 256 or even 1,024 tokens. This translates to a significant speedup in training and inference, making image generation much more efficient.
That's incredibly impressive, Dr. Yu. It sounds like you're essentially making image generation more accessible by reducing the computational demands. Could you elaborate on how TiTok works and how you achieve this significant compression?
Sure. TiTok utilizes a vision transformer, or ViT, architecture for both encoding and decoding images. During encoding, we first divide the image into patches. Then we concatenate these patches with a sequence of latent tokens. This combined representation is fed into the ViT encoder. The key here is that we only retain the latent tokens from the encoder output, creating a 1D sequence that represents the entire image. This is what gives us the compression advantage. During decoding, we use a vector quantizer to translate these latent tokens into discrete representations, and we add mask tokens to guide the VT decoder to reconstruct the original image. We found that with as few as 32 tokens, TiTok can capture enough information to reconstruct and generate very high-quality images.
This is fascinating. It seems like you're effectively teaching the model to understand the image's content and relationships between its parts, allowing for a more efficient representation. This is where your two-stage training paradigm with proxy codes comes in, right?
Yes, that's correct. We've developed a two-stage training approach that significantly improves TiTok's performance. In the first stage, we utilize proxy codes generated by a pre-trained mask-git VQN model. This provides a starting point for training, allowing us to focus on optimizing the 1D tokenization process without the complexities of typical VQGAN training. This warm-up stage is crucial for getting our model off to a good start. In the second stage, we fine-tune the decoder specifically to generate pixel-level output. This results in a more accurate and visually appealing reconstruction. We found that this two-stage training strategy significantly boosts both reconstruction and generation performance.
Professor Kremers, from a broader perspective, what are the implications of this shift from 2D to 1D tokenization for image generation and computer vision? Is this a paradigm shift? Absolutely. This is a major leap forward. Think about it. For years, we've been stuck with the 2D grid model, but it was inherently limiting. TiTok, with its 1D representation, opens up a whole new world of possibilities. It's not just about efficiency, it's about enabling new levels of detail and complexity in generated images. This shift could lead to breakthroughs in areas like photorealistic image editing, creating more detailed and realistic virtual environments, and even enhancing applications in fields like medical imaging and scientific visualization. Dr. Yu, you've mentioned that TiTok outperforms existing methods in various benchmarks. Can you delve into the experimental setup and results? How did you compare TiTok with other approaches, and what were the key findings?
We conducted extensive experiments on ImageNet, a standard benchmark for image generation. We compared TiTok with various baselines, including MaskGit, VQGen, VQN diffusion models like LDM4 and DiTXL2. We evaluated the models using reconstruction RFID, generation inception score IS, and sampling speed. Our results were quite remarkable. TiTok significantly outperformed all other methods in terms of generation quality, achieving comparable or even better GFID scores while using significantly fewer tokens. This led to a dramatic speedup in both training and inference, with up to a 410x increase in sampling speed compared to DiTXL2.
That's astounding. It seems like you've effectively broken the barrier between speed and quality in image generation. What insights did you gain from your ablation studies, and how do they reinforce your core findings?
Our ablation studies provided valuable insights into the design choices for TiTok. We explored the impact of factors like codebook size, training epochs, decoder fine-tuning, and masking schedules. We found that increasing the codebook size and extending training epochs improved reconstruction performance, while decoder fine-tuning significantly boosted both reconstruction and generation quality. We also discovered that TiTok's preference for the Arcos or linear masking schedules differed from the original MaskGit findings, highlighting the unique characteristics of 1D tokens. These studies solidified our understanding of TiTok's strengths and pointed towards future optimization possibilities.
Professor Kremers, what are the potential limitations of TiTok, and what are the next steps for this research? While TiTok demonstrates immense promise, there are areas for further research. Currently, we've primarily focused on the VQ tokenizer formulation and the MaskGit framework. It's crucial to explore the applicability of 1D tokenization to other tokenizer formulations and generation frameworks, including diffusion models. Additionally, we need to address the potential biases and ethical considerations associated with generative models, ensuring fairness and responsible use. We're also looking into optimizing classifier-free guidance for 1D compact tokens, which could lead to even faster inference times. And of course, we're eager to explore the potential of TiTok for other modalities beyond images, such as video. Dr. Yu, what are the broader impacts of this research, and what potential applications do you see for TiTok in the future?
This research has the potential to revolutionize image generation, making it more accessible and efficient. TiTok's ability to achieve high-quality results with significantly fewer tokens opens up opportunities for applications in various fields. Imagine text-to-image generation models that generate more realistic images faster, or image editing tools that allow for more sophisticated manipulation with minimal computational overhead. TiTok could also enhance image compression techniques, particularly in applications where bandwidth or storage space is limited. It could even be applied to content creation workflows in industries like graphic design, advertising, and fashion, enabling faster and more efficient production processes.
It's clear that TiTok represents a significant step forward in image generation and computer vision. Dr. Yu, Professor Creamers, thank you both for sharing your insights and expertise with our listeners. This has been an incredibly informative and exciting discussion. We're eager to see what the future holds for 1D tokenization and image generation.
It was a pleasure to be here.
Thank you for having us.